Hello everyone, Brian Wood here again for another exciting edition of Fun with BenchVue. Today we're going to do something a little different. We're going to hook up a data acquisition unit to a device under test, in this case an audio amplifier circuit, and that will allow us to take multiple measurements on the device under test. So this is particularly useful if you're trying to do remote teaching, remote learning, you're trying to learn how a circuit works, but you don't have access to the hardware. And so you have to log in remotely, get in through the virtual private network into your system. But assuming you can do all that, the data acquisition unit has an internal voltmeter. It has a bunch of switches. It allows you to multiplex various signals in and out to different equipment to do measurements. So it's very handy. So that's what we're going to do today. And we're going to use BenchVue to control it and several instruments to do the measurements. Let's get started.
Okay, let's have a look at our circuit under test. This is a one transistor audio amplifier consisting of an NPN transistor, an input coupling capacitor, C1, a bias network, R1, R2, an emitter resistor, RE, a bypass capacitor, C2, and a load resistor, RL. Now, what kind of measurements might we want to take on this circuit? We'd like to measure the base voltage, the collector voltage, the emitter voltage, the base current, and the collector current, both AC and DC. We'd like to, from that, calculate the collector emitter voltage, power dissipation, the beta, and the voltage gain. We'd like to change the input bias network to try different bias points and see the effect on distortion as the Q point is varied. We'd like to remove C2 and analyze the effect of AC versus DC gain. And finally, we'd like to be able to measure total harmonic distortion, which is a good figure of merit for any audio amplifier. Now, that's a lot of measurements to be taking on a little circuit like this. If you're in a lab and physically able to move a probe around, then you can easily take multiple DMM and scope measurements on every node in the circuit. Doing that remotely is a lot more difficult. You have to pre-wire a voltmeter or other measurement equipment and stimulus equipment to this device under test ahead of time so that they can be accessed remotely. And a data acquisition box is a great way to do that. The DAQ970 has room for 3 plug-in cards of various types and also includes a high-performance internal DMM. Let's see how we need to hook this up. The blue boxes represent wiring that will occur inside the data acquisition unit. Power supply, function generator, a loop to measure base current, a loop to measure collector current, and a way to connect the bypass capacitor. Now let's look at this in a little more detail. It helps to color code the wiring. So I'm using red for power supply, blue for an input signal, orange to connect the base circuit up as well as the base resistor to ground for biasing, and then brown to bring the current measurement back to the base. So you can see that one channel is allocated as a current measurement channel. Yellow for the top of the collector and purple for the bottom. That also includes a current measurement circuit. I'm using a white wire on the emitter to connect those points up, and you can also see a way to disconnect or connect C2. And of course, the ground circuits are all in black. So really there's only 9 colored wires here. You can connect any other interconnects inside the data acquisition unit itself. Here's what the cards look like, and you can see how nice it is to have color-coded wires in here, so it's very easy to find everything. There's also a little prototyping room for, in this case, the resistors. Now here's the actual circuit under test, showing my breadboard. There's transistor Q1, input coupling capacitor C1, the top of the resistor biasing network, R1, the emitter resistor, RE, the emitter bypass capacitor, CE, and the load resistor, RL. Now you see some other interesting parts in here. These are toroids. These are in fact FT3743 types. Often you'll find that when running this many wires in and out of a circuit, it can cause the circuit to oscillate because they're acting as antennas. There's capacitive and inductive coupling between the leads, and the inductors are a great way to stop that from happening. All right, let's fire up BenchVue and see what happens. First, we're going to start the DAQ app, and this is going to come up with nothing defined. I want to start from scratch so that you can see the process I'm using, and then I will load a state file to save some time to show that you can save all this information in a state file. Okay, so we have no computed channels, we have empty modules with no definitions in them. Step one is to first make sure that you've got the modules that you want to use in the instrument. So we have a scan module, a 20-channel armature multiplexer in slot 1 and 2. I'm actually not going to be using slot 2. Slot 3 is a general purpose actuator relay module, the DAQ970A. And we can define all of those. It came up and recognized them anyway, so that's all done. Data logging, what I'm going to do here is tell it to start with the start button. Let's use a 1-second time delay in between readings, just because we don't want to take them all that fast, or we're going to hear a lot of relays clicking. We don't have a digitizer. We're going to stop data logging immediately with the stop button. So it'll start and stop when we hit the start button down here. Okay, now to configure the channels, I want to do channels 101, 102, 103. This is going to be, you can put a name on them, so let's make that base voltage, emitter voltage, collector voltage. Now, one of the things that is a little unique about this is that I can't change the function while I'm scanning. I can predefine it to be DC voltage, but if I wanted to change that particular reading on channel 101, it's connected to the base. If I wanted to do an AC voltage measurement on it, I would be only doing an AC voltage measurement on it. Now, there is a way in TestFlow to handle this by loading different state files. So you could define all of these, go down here to the bottom and save the instrument state, then come back up here and redefine them to use AC voltage. An easier way, if you have enough channels allocated, is to just reallocate the same point on your circuit. So two relays going to one point, 101 and 104, are both connected to the base, but in one case I'm going to do a DC voltage measurement. In the other case, I'm going to do an AC voltage measurement. So same with the collector voltage, and I want to measure AC. Okay, the two current channels are down here at 121 and 122, and I'll just define those as base current and collector current. That's how you set this up. You can also change the number of digits of resolution. You can tell it to generate alarms if things go out of range. But for this simple experiment, all we really want to do is measure some DC voltages, DC currents, and AC voltages. Now let's look at the setup for the 20-channel actuator general purpose switch card in slot 3, which is a DAQ970A. These are general purpose relays. They can be used for anything, and you can open or close any of them while the scan list is in progress. So we've predefined the names of these. Power supply high is the power to Q1, Q1 being the only transistor in this circuit, but you could have more than one. So it's good practice to name them starting at 1. Power supply low to ground. Function generator high to input of Q1. Function generator low to ground. Then the emitter bypass capacitor CE on Q1. And then we have the resistor stick. These are the lower half of the input bias network that allows us to change the bias point on the transistor. So that's R2. The first value is 1K. Then we have 2.2K. 4.7K. 7.5K. And 10K. Then I skipped a couple of relays and allocated 313 and 314 to the scope. So there's scope high, collector voltage Q1, and scope low to ground. Now, once these are all defined, we want to initialize the state, and I'd like for these to wake up connected. So I want to connect the power supply, the function generator, close the capacitor, and then of these 5 resistors here, I'll choose the 10K resistor as a pull down and go ahead and connect the oscilloscope. Okay, let's have a look at what it takes to set up the graphics window. It's the third tab along the top. There are a bunch of gadgets that you can select to put in this graphics window, such as a strip chart, an XY chart, a histogram, a data grid, a reading gadget, and so on. We're going to want the switch gadget, so let me pick one. Anytime you have a gadget in here, there are gadget properties associated with it that you can activate over on the right. So here we've defaulted to the power supply high relay. I'd actually like that box to contain both the power supply high and low. And I'd like another one with the function generator high and low. So we'll pick the function generator high input and the function generator low to ground. So that's the process by which you can add these relay gadgets to the graphics window. The other one we're going to want is the data grid. This one allows us to look at a whole bunch of scanned channels all at the same time. So for example, it's defaulted to channel 101, the base voltage. We can add the collector voltage and so on, and then see the readings all at the same time. Now, I've already done one of these once, so I'm going to show you that you can load the instrument state by coming down here at the bottom and picking a state setup that you've previously saved. And this will save all of the relay configurations as well as the graphics setup. So it's more than just the relay definitions that are saved inside the DAQ970. It's also the BenchVue state information about position of windows and things like that. All right, so as you can see, we've loaded the information about the relay configuration on all the channels, and over in the graphics setup you see the position of everything. So power supply, function generator, oscilloscope, the emitter bypass capacitor, and the input bias resistors, and then of course the data grid. Now you may wonder where the beta, the voltage gain, and the power entries came from, If we go back to the Configure Channels tab, you'll see that under Computed Channels, I have defined channels 901, 902, and 903 as beta, voltage gain, and power. So how did we get to these various quantities? You can simply enter a name here. I entered the term beta, and I want it to be a mathematical function. So by clicking the ... we get the computed channel dialog box, which lets you pick various types of formulas. A basic math formula, divide argument 1 by argument 2. In this case, collector current divided by base current is beta, and it doesn't have any units. So instead of picking a unit, we just left it at none. For the voltage gain, it's a similar formula. It's again a divide operation, but we're going to divide the AC voltage on the collector by the AC voltage on the base. And again, that has no units, so we've selected none. Power is a little bit more involved. Here, we want to actually bring up the general equation editor and put a more complicated formula in there. So here we want to take something from this list of available channels, which is going to be the collector voltage minus the emitter voltage, that quantity times channel 122, which is the collector current. The result of that would be power, and so we've selected watts for the unit. All right, it's ready to run at this point, so let's just go ahead and start it. We'll click the Start button. I'll move the microphone over near the DAQ970 so you can hear the relays actually clicking. All right, let's have a look at the readings. Now there's a 12-volt supply going into the circuit, and a 1K load resistor and a 1K emitter resistor. So the DC bias point, it will be the base voltage, 5.8 in this case, using the R2 of 10K over here. If we subtract 6 or 7 tenths of a volt for the base emitter diode junction, then we'd expect the base or the emitter voltage to be about 7 tenths less than that, and it is 5.1. It's going to result in 5 milliamps of collector to emitter current. Well, 5 milliamps going through a 1K resistor is 5 volts, so we'd expect the collector voltage to be 12 minus 5, or about 7. If we look at the collector voltage, you can see it is about 7. The base current is running about 27 microamps, and there's the 5 milliamps of collector current. You divide those two, you're going to get the volt, or the beta of the transistor, which is about 187 right now, and the voltage gain with this configuration is running about 40. The power dissipation is well within the spec of the 2N3904. As you remember, that's the current times the collector emitter voltage. So that is 9 milliwatts, well within the power dissipation rating of the transistor. Okay, now the real trick at this point is to change things and note what the effect is. So we could try a different bias resistor. Let's click that one and take that one out. So now we've got a 10K pull up and a 4.7K pull down. You can see that the base voltage has lowered down to 3.8 volts, and the emitter voltage is again about 6 or 7 tenths less than that. So we are seeing an effect as we change the parameters in the circuit. Notice what happens now if I disconnect the emitter bypass capacitor, which will eliminate all of the AC gain in the circuit, and the emitter resistor and the load resistor are the same value, 1K, so you'd expect a voltage gain of about 1, a little less than 1 actually, and sure enough it's reading 0.8. So it's very easy in BenchVue to make changes in the setup and then evaluate the results. Let's take a look now at what happens visually. We want to turn the instruments tab back on so that you can see we've got the function generator and the oscilloscope enabled. Let's take a look at all three of these instruments at once. So there's kind of a compressed look over here on the right of the DAQ, and the function generator, you can see we're set to 5 millivolts peak to peak and a 1 kilohertz frequency. And there's the oscilloscope. All right, let's expand the oscilloscope and do a get current screen on it. You can see the output waveform here centered in the scope screen. I've also enabled the total harmonic distortion measurement, and so you can see the peak of the fast Fourier transform analysis at 1 kilohertz and the harmonics. These are in purple. So the second harmonic, third harmonic, and so on. It's a very simple calculation to take the amplitude of these, run it through a formula to calculate total harmonic distortion, and this measurement is done for you in the oscilloscope. So with this configuration, we're seeing 0.7%, and it varies a little bit because there's a little bit of noise in the circuit here. So the total harmonic distortion calculation will be approximate, but you can really see when you make dramatic changes. For example, let's go change the amplitude here to 20 millivolts peak to peak. Now this is going to take the waveform off screen in the oscilloscope. If I were to look at the current screen here, you'll see that it's pegging, the top and the bottom are pegged. That will not result in a reasonable measurement of total harmonic distortion, so we need to lower the amplitude there. So we need to go into the instrument settings tab and change the volts per division down to something a little more reasonable. We'll go back to the screen image, get the current screen, and now you can see that the total harmonic distortion with this set of conditions has gone up. It's 2.4%. When you do raise the amplitude or change the bias voltage enough, you can actually start to see the distortion. You will move the Q point down to a point that's too low, and you'll actually be able to see the distortion. One thing I haven't shown yet is how to access the instruments remotely. I have a separate video available on that, and I'll put a link to that here on the screen in a second. But if you go into Connection Expert to define your instruments and click the gear and then hit Settings, you'll see that there's a way to enable a remote I/O server and auto start it on machine startup if you want. This remote server will allow anything connected to that PC to be put on LAN. So it's pretty easy to just click this checkbox, take note of the IP address of this PC, and then use Connection Expert on the remote PC, the client PC that the students are using, to tell it where to get the instruments. Here's a link to the video on YouTube showing how to set up BenchVue for remote access.
Well, thanks for watching this video on how to set up a circuit under test remotely in these times when we're all working from home and trying our best to continue learning how electronics works. It's a real challenge, but as you can see, it's not that difficult to set up a data acquisition system to capture multiple points on your circuit under test and give you remote access anywhere in the world. This has been the second in a series on Fun with BenchVue. We'll have more coming later. Thanks again for watching. See you next time.